This is problem 23 from chapter 18. The coefficient of kinetic friction between the 100-pound disc and the surface of the conveyor belt is 0.2. If the conveyor belt is moving with a speed of 6 feet per second when the disc is placed in contact with it, determine the number of revolutions the disc makes before it reaches a constant angular velocity. If it's a constant angular velocity, the angular acceleration is equal to 0. And we're going to use the work energy conservation law here. The change in height for the mass center is equal to 0. So I can say T1 plus the work is equal to T2. It might actually be helpful here to draw a free body diagram. So I have the force of gravity acting downwards. I have the normal force acting upwards. Neither of those forces do work. And I have a force of kinetic friction acting to the left, which does do work. And because the mass center of the disc is staying at the same height, it's not moving in the y direction, the acceleration in the y direction is equal to 0, and I can say the normal force is equal to m times g, which means the force of kinetic friction is equal to the coefficient of kinetic friction times mg. Here actually they called it mu sub a, so maybe we want to call that u sub a also. Okay, now we're going to assume that the wheel is starting from the disc is starting from rest, so T1 is equal to 0. Then I need the work done by the force of friction. The force of friction is constant as long as it's kinetic friction, which it's going to be up until the wheel begins to move at a constant velocity, which would be rolling without slipping. So for my work, I can pull that constant force outside, so the work is just equal to the force, whoops, this is plus, the force of kinetic friction times, let's call that delta S. Okay, and then this is equal to the final kinetic energy, which is the mass center of the disc is not moving, so it's just 1/2 times the moment of inertia times omega squared. Okay, so when the angular acceleration is equal to 0, that's the moment when the disc begins to, when it stops slipping on the conveyor belt. And at that instant, omega times r is equal to the velocity of the conveyor belt. So when the disc stops slipping, the angular velocity times the radius of the disc is equal to 6 feet per second. So we can take our equation here, and for the moment of inertia for the disc, that is, you can look it up in the back of the book, 1/2 mr squared. So this is 1/2 the mass times the radius squared. Angular velocity from what we have here, that's the 6 feet per second squared divided by r. And then this r in the denominator is squared, this r is also squared, so those cancel each other out, and this is 1/4 the mass times 6 squared, that's 36. Okay, and then you have to be careful with this delta S here. That's actually the same as the distance that the conveyor belt travels from the point where the wheel was put down up until it starts moving at a constant velocity, or if you look at this point here, it's how far it travels around. So we want to relate this delta S to the change in angular position, which we can do using the arc length formula. So the distance that a point on the wheel travels is equal to the radius of the wheel times the change in angular position. Okay, so this is FKF, that's mu A mg, and then delta S is r times delta theta. And I'll just write that again down here. The mass cancels out. We're not really looking for delta theta, but we're going to find delta theta first. And then we're going to find the number of revolutions. So delta theta is equal to 36 divided by 4. Then bring the mu A G R over to the other side. The coefficient of kinetic friction is 0.2. G is 32.2 feet per second squared. And R, if we go back to the picture here, is 0.5 feet. And so for delta theta, we get 2.795. Then if you want the number of revolutions, take delta theta and divide it by 2 pi. So this is 2.795. Radians divided by 2 pi radians gives you 0.4448. That is the number of revolutions, and that concludes problem 23.